In 1957, astronomers cataloged a faint smudge in a photographic sky survey. They labeled it Tonantla Object Number 618, a dot on a glass plate. It looked like a star. It was listed as a star, but over the following decades, as instruments improved and measurements grew more precise, something became impossible to ignore. The object was not a star at all. It was something far stranger, far older, and almost incomprehensibly more powerful. What they had accidentally recorded was one of the most extreme objects the universe has ever produced. To understand what makes TON 618 so unusual, you first need to understand what it actually is. It is a quasar. That word is short for quasi-stellar radio source, and the name comes from the early days of radio astronomy when these objects appeared star-like in optical images, but emitted energies that no star could explain. What a quasar actually represents is a supermassive black hole in the process of actively consuming the material around it. Not a dormant black hole, not a quiet one, a feeding one. Here is how that feeding process works. At the center of a galaxy, a black hole exerts gravitational force on everything nearby. Gas clouds, dust, debris, even stars that wander too close all get pulled toward it. But that material does not simply fall straight in. Conservation of angular momentum causes it to spiral inward in a flattened rotating structure called an accretion disk. As the gas and dust spiral closer and closer, they accelerate. Particles collide with each other at increasing speeds. Friction converts kinetic energy into heat. The temperature inside this disk climbs to tens of millions of degrees Celsius. At those temperatures, matter does not merely glow. It radiates across the entire electromagnetic spectrum simultaneously. X-rays, ultraviolet radiation, visible light, infrared radio waves. All of it pouring outward from this single region of space at the galaxy's core. The energy output becomes so vast that it can outshine every single star in the host galaxy combined. Hundreds of billions of stars, each one a nuclear furnace burning for billions of years, and the quasar at the center outshines all of them together. That is what we mean when we call these objects among the brightest things in the observable universe. TON 618 sits at an extraordinary distance from Earth. When astronomers measure its position in an expanding universe, accounting for the way space itself has stretched since the light left its source, they calculate that TON 618 is approximately 18.2 billion light-years away in comoving distance terms. But here is what that number actually means for what we observe. The light we detect when we look at TON 618 today left its source approximately 10.8 billion years ago. The universe at that time was roughly 3 billion years old. We are now living in a universe that is approximately 13.8 billion years old. That means when you look at images of TON 618 taken by modern telescopes, you are not seeing it as it exists today. You are seeing a snapshot of it as it was more than 10 billion years in the past. The light carrying that image has been traveling through space, through an expanding universe, past forming galaxies and dying stars, for over 10 billion years before arriving at your instruments. The present-day state of TON 618 is completely invisible to us. Its current light will not arrive for another 10.8 billion years. By that time, the Sun will be long dead. Earth will likely no longer exist in any recognizable form. Whatever TON 618 looks like right now is knowledge that no human civilization, as currently conceived, could ever possess. But what we can see from that ancient light is extraordinary enough. Because at the heart of that distant quasar sits a black hole with a confirmed mass of 66 billion times the mass of our Sun. Let that number breathe for a moment. 66 billion solar masses. To build intuition for what that means, start with our own Sun. It contains enough mass to generate gravity that holds 8 planets in stable orbits across billions of kilometers of space. It accounts for roughly 99.8% of all mass in the entire solar system. Planets, moons, asteroids, comets, and the solar wind together make up only the remaining fraction. Our Sun has a mass equivalent to approximately 333,000 Earths. It is immense on any human scale of reference. Now compare that to the black hole at the center of our own Milky Way galaxy. That black hole, named Sagittarius A star, has a mass of approximately 4 million solar masses. It is the gravitational anchor of an entire galaxy containing hundreds of billions of stars. The influence of its gravity extends across tens of thousands of light years. And yet, measured against Ton 618, Sagittarius A star is more than 16,000 times less massive. Before the era of modern quasar studies, the black hole that commanded the most attention for its sheer size was M87 star, the one famously imaged by the Event Horizon Telescope collaboration in 2019. That orange ring of glowing gas surrounding a dark central shadow made headlines around the world and became one of the most recognized images in modern science. M87 star has a mass of 6.5 billion solar masses. It is one of the most massive black holes ever directly imaged. Ton 618's black hole is more than 10 times more massive than M87 star. The only candidate that might exceed it is a more recently identified object called Phoenix A, estimated at roughly 100 billion solar masses. But those measurements carry significant uncertainty and ongoing debate. Ton 618's mass is confirmed through multiple independent measurement techniques, making it one of the most reliably measured ultramassive black holes known to science. When we work out what 66 billion solar masses translates to in terms of the total number of Earths, the figure becomes almost linguistically awkward to state clearly. Our Sun is 333,000 times the mass of Earth. Multiply that by 66 billion and you get approximately 22 quadrillion Earth masses. That is 22 followed by 15 zeros. If you tried to line up objects each as massive as planet Earth side by side, until you reached the total mass of Ton 618, that line of planets would stretch across the observable universe not once, not twice, but millions of times over. Now let's talk about the physical size of this black hole, because mass alone does not fully communicate scale. Every black hole has a boundary called the event horizon. This is not a physical surface. There is no wall, no membrane, no edge you could touch. It is simply the mathematical point of no return, the boundary inside which the escape velocity required to leave exceeds the speed of light. Nothing that crosses this boundary can ever return to the outside universe. Not matter, not radiation, not information. For a black hole with the mass of our Sun, the event horizon would have a diameter of approximately 6 kilometers, a sphere smaller than a medium-sized city. For the black hole at the center of the Milky Way, the event horizon is roughly 24 million kilometers in diameter, which sounds large until you realize that the Sun itself is 1.4 million kilometers wide. So we are talking about a sphere roughly 17 times the diameter of the Sun. For Ton 618, the event horizon has a diameter of approximately 2,600 astronomical units. An astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. It is the standard ruler we use to map out our solar system. Earth orbits the Sun at 1 astronomical unit. Mars orbits at about 1.5 astronomical units. Jupiter, the largest planet in our solar system, orbits at 5.2 astronomical units. Saturn, with its iconic ring system, orbits at about 9.5 astronomical units. Uranus orbits at roughly 19 astronomical units. Neptune, the outermost recognized planet, orbits at approximately 30 astronomical units from the Sun. Ton 618's event horizon spans 2,600 astronomical units across. That is more than 40 times the orbital distance of Neptune. If you place Ton 618's black hole at the center of our solar system, where our Sun currently sits, its event horizon would extend far past Neptune in every direction. Past the Kuiper belt, past the inner reaches of the Oort cloud. Every planet in our solar system, every dwarf planet, every asteroid, every comet currently orbiting our sun, all of it would fit inside the event horizon with room to spare. 40 complete solar systems, stacked end to end from edge to edge, would fill that space. There is another way to appreciate this scale, and it involves light speed. Light travels at approximately 300,000 kilometers per second. At that speed, light covers the distance from Earth to the Moon in about 1.3 seconds. It crosses the distance from Earth to the Sun in 8 minutes. It takes about 16 minutes to cross the width of Earth's entire orbit around the Sun. Light crosses the full diameter of Neptune's orbit in about 8 hours. To cross from one side of TUN 618's event horizon to the other, traveling at the speed of light, takes approximately 11 days. 11 days at 300,000 kilometers per second. That is the size of this thing. And it grew to this size in what cosmologists consider a remarkably short time. The universe was approximately 3 billion years old when the light we see left TUN 618. By that point, the black hole had already accumulated 66 billion solar masses. This creates one of the genuine unresolved puzzles in modern astrophysics. Black holes grow by consuming matter. Every time gas falls across the event horizon, every time a star gets torn apart by tidal forces and its debris spirals in, the black hole gains mass. But this process is self-limiting in a way that makes TUN 618 deeply puzzling. When a black hole feeds, the infalling matter does not simply vanish silently. The accretion disk radiates enormous energy. Some of that energy pushes outward as radiation pressure, working against the infall of new material. There is a theoretical limit to how fast a black hole can grow while emitting at its maximum luminosity. This is called the Eddington limit, named after the British astrophysicist Arthur Eddington, who first derived the relationship between radiation pressure and gravity in this context. The Eddington limit essentially describes a balance point. The outward push of radiation from the accretion disk and the inward pull of gravity reach equilibrium. A black hole feeding at exactly the Eddington rate is said to be accreting at the Eddington limit. Theoretical models suggest that even under the most favorable conditions, growing a black hole from stellar-scale origins to something like TUN 618's mass within 3 billion years requires sustained, near-maximum feeding for essentially the entire time. Some theorists argue the seed black holes in the early universe would need to start with much greater initial masses than typical stellar mass black holes to explain objects like TUN 618. One proposed pathway involves the direct collapse of massive primordial gas clouds into black holes, bypassing star formation entirely. In this scenario, under specific conditions in the early universe where molecular hydrogen cooling was suppressed, an enormous gas cloud could collapse directly into a black hole, with an initial mass tens of thousands or even hundreds of thousands of times that of the Sun. Starting with such a massive seed gives the black hole a significant head start. Another possibility involves periods of super-Eddington accretion, where the black hole feeds faster than the theoretical limit would seem to allow. Certain configurations of accretion geometry, combined with powerful outflows that carry away excess radiation, might permit brief but intense episodes of feeding that exceed the standard Eddington rate. If these episodes were common in the early universe, they could partially explain how black holes grew so quickly. A third possibility, perhaps the most unsettling from a theoretical standpoint, is that some combination of both effects occurred simultaneously, and that our current models of black hole growth are missing important physics. TUN 618 did not grow slowly. The universe at 3 billion years old was already capable of producing black holes of this scale, and our theories are still working to catch up. While it was growing, TUN 618 was not quiet. During the quasar phase, when its accretion disk was full and actively consuming material at an enormous rate. Its luminosity was approximately 140 trillion times the luminosity of our Sun. 140 trillion. Our Sun's luminosity provides all the energy necessary to sustain complex chemistry, liquid water, weather systems, and life on a planet 93 million miles away. It is bright enough that direct observation from Earth without protection causes immediate eye damage. It lights the outer solar system well enough for probes billions of kilometers away to still receive faint solar energy. And TUN 618, during its active phase, was outputting energy at 140 trillion times that rate. To put that in concrete physical terms, our Sun produces approximately 3.8 times 10 to the 26th watts of power continuously. 140 trillion times that figure comes to approximately 5.3 times 10 to the 41st watts. This is energy on a scale that simply has no intuitive equivalent in human experience. It is the kind of number that physics can calculate and mathematics can represent, but which refuses to map onto anything we can picture. Even after traveling for more than 10 billion years, even after the light spread out across an expanding universe and lost energy to cosmological redshift, we can still detect it. The light from a source active over 10 billion years ago, at a distance of over 10 billion light years, reaches our telescopes as a detectable signal. That is the original brightness translated across cosmic time. Quasars like TUN 618 were not evenly distributed across cosmic history. They were concentrated in a specific era. Observations show that quasars were most numerous when the universe was between about 2 and 4 billion years old. This is sometimes called the quasar epoch, or the era of peak black hole feeding. During this period, the universe was still rich with the raw fuel that black holes need. Galaxies were still assembling from clouds of gas. Collisions and mergers between early galaxies were common, and these events funneled enormous amounts of material toward galactic centers. Black holes at those centers had access to fuel in quantities that later, more settled galactic environments would not provide. As the universe continued to expand and age, galactic collisions became less frequent. Much of the available gas had either been converted into stars, blown out of galaxies by the intense radiation of active quasars themselves, or simply spread too thin to feed the central black holes efficiently. One by one, quasars faded. The accretion disks thinned. The feeding slowed. Today, most of the black holes that once powered quasars sit dormant or nearly so at the centers of galaxies. They still have enormous mass. They still warp spacetime around them, but the feast is over. The black hole at the center of the Milky Way is a probable example of this life cycle. Sagittarius A star today is mostly quiet. It produces occasional flares when small amounts of gas pass too close, and astronomers observed a significant event in 2019 when a gas cloud called G2 passed within the black hole's influence and triggered brief activity. But these are minor episodes compared to what the Milky Way's center must have looked like billions of years ago. Most evidence suggests that our galactic center once hosted a quasar, perhaps 2 to 4 billion years after the universe's formation, and that this activity has since wound down almost entirely. TUN 618 may have followed the same trajectory. The light we see from it shows an active quasar at peak feeding, but that light reflects the state of things over 10 billion years ago. The black hole has likely not grown substantially since then, because the conditions that allowed such rapid early growth no longer exist in the modern universe the way they did during the quasar epoch. Whether it is still technically a quasar today, whether any accretion disk remains, whether it occasionally flares or sits entirely silent, we cannot say. We cannot see it. There is a profound asymmetry at the heart of observational astronomy that TUN 618 illustrates more sharply than almost any other object. We look at the sky and we see the past, not a recent past, not a few seconds or a few years. When we study objects at cosmological distances, we are reading a historical record written in light that left its sources billions of years before Earth itself existed. The Andromeda Galaxy. Our nearest large galactic neighbor is about 2.5 million light-years away. The light reaching us from Andromeda tonight left that galaxy 2.5 million years ago, when early hominids were just beginning to emerge on the African continent. That gap, 2.5 million years, feels vast by human standards. By cosmological standards, it is practically instantaneous. TUN 618 is over 4,000 times farther away than Andromeda. The temporal gap between what we see and what is actually happening there now is not 2.5 million years. It is over 10 billion years. The universe itself was barely a fifth of its current age when the photons we detect today began their journey. We are not observing the cosmos as it is. We are observing layers of its history, each layer corresponding to a different distance, a different epoch, a different state of universal evolution. This is not a limitation that better technology will overcome. It is a fundamental feature of how information travels through space. Light has a finite speed. The universe has a finite age. Distant objects are separated from us not only by space but by time, and these two separations are inseparable. Even if humanity somehow survived for billions of years and built telescopes of unimaginable sensitivity, we would still be looking at TUN 618 as it existed billions of years ago, because that is the only light available for us to observe. The present-day photons from that location are still en route. This also means that every deep sky survey, every catalog of distant galaxies and quasars, is simultaneously a catalog of different historical moments in universal evolution. When astronomers study objects at different distances, they are effectively taking core samples through cosmic time. Objects at a certain distance show the universe at one particular age. Objects farther away show it younger. Objects closer show it older. TUN 618 sits near the edge of what we can observe, and when we look at it, we are reading a page from near the beginning of the story. The astrophysics community continues to study ultramassive black holes like TUN 618 for multiple interconnected reasons. Understanding their growth rates and formation mechanisms is directly connected to understanding how the first galaxies formed. The relationship between a galaxy and the supermassive black hole at its center is not incidental. The two appear to co-evolve. There is an observed correlation between the mass of a galaxy's central black hole and the properties of the galaxy's stellar bulge, suggesting that the growth of the black hole and the growth of the galaxy regulate each other through feedback processes. When a quasar is active, its radiation and the powerful jets it sometimes produces can heat and expel gas from the host galaxy. This quasar feedback can actually suppress star formation across the entire galaxy, effectively using the energy from the feeding black hole to slow down the galaxy's own growth. Understanding this feedback mechanism at extreme scales, as seen in systems like TUN 618, helps explain why galaxies of different masses have the properties they do today. There is also the question of what happens at the very upper end of the black hole mass spectrum. We now know black holes can range from a few solar masses, the remnants of collapsed massive stars, up through millions and then billions, and apparently even tens of billions of solar masses. But is there a physical upper limit? Is there a point at which a black hole simply cannot continue growing? What terminates the quasar phase? Is it purely the exhaustion of available fuel, or do additional physical processes play a role? Objects like TUN 618, at the extreme end of the observed mass distribution, provide empirical constraints for theories trying to answer these questions. The measurement of TUN 618's black hole mass was itself a remarkable achievement. It was derived using a technique called reverberation mapping. When a quasar is active, The accretion disk emits ultraviolet radiation that illuminates clouds of gas farther out from the black hole. These gas clouds absorb the ultraviolet light and re-emit it as optical spectral emission lines. The key insight of reverberation mapping is that there is a time delay between the UV emission from the disk and the response in the emission lines from the surrounding gas clouds. This delay corresponds to the light travel time between the disk and the gas clouds. By measuring the delay and combining it with the velocity width of the emission lines, which reflects the orbital speed of the gas clouds under the black hole's gravitational influence, astronomers can calculate the black hole's mass. Applying this technique to TON 618, multiple independent studies have converged on a mass in the range of 60 to 66 billion solar masses. The consistency of these independent measurements gives astronomers high confidence in the result. What makes the measurement additionally significant is its age. The mass we are measuring is not TON 618's current mass. It is the mass it had approximately 10.8 billion years ago. This is the only mass measurement we will ever be able to make of this object, because those are the only photons from it that have ever reached us and ever will reach us within any foreseeable future of scientific observation. In a broader context, TON 618 is one of several quasars that have reshaped our picture of the early universe over the past several decades. Before the systematic study of high-redshift quasars became possible through large-scale sky surveys and sensitive spectrographs, there was a general assumption that the very early universe was a simpler, less structured place. What the observations have revealed is something considerably more dramatic. The early universe was in many respects more extreme than the universe we inhabit today. Black holes had already grown to tens of billions of solar masses. Galaxies had already formed and begun their own evolution. The universe at 3 billion years old was not a quiet, featureless expanse of gas slowly condensing. It was already home to some of the most energetic processes we can observe anywhere across cosmic time. This has forced continuous revision of cosmological models and galaxy formation theories. The universe's early chapters were not calm. They were active, violent, and in certain respects more productive of extreme objects than any subsequent era. The conditions that existed when matter was denser and gas supplies were more abundant led to the formation of structures that the modern universe, with its more dilute distribution of gas and its more widely separated galaxies, cannot easily replicate. This also has implications for how we think about the observable universe's limits. We can only observe out to the distance from which light has had time to reach us since the Big Bang. This region is called the observable universe, and its radius is approximately 46 billion light-years. Within that sphere, we can, in principle, detect signals from any object. TON 618, at about 18.2 billion light-years, sits well within that observable horizon. But the deeper we look, the older the light, and the more we are looking at a universe that no longer exists in the form we observe. The matter that once made up the quasar TON 618 is still out there somewhere. The black hole still exists. The galaxy surrounding it still exists. The processes of stellar evolution and galactic dynamics have continued for 10 billion years since the light we see left that system. We just have no way of receiving any report from it. The gap is absolute. The separation is total. There is something genuinely interesting in the philosophical dimension of this situation, independent of the physics itself. The ancient light from TON 618 carries real information. It is not a metaphor or an approximation. Those are actual photons that interacted with the accretion disk of a 66 billion solar mass black hole over 10 billion years ago and have been traveling since, carrying encoded information about that interaction in their frequency, their polarization, their arrival pattern. When astronomers record that light with spectrographs and photometers, they are performing a measurement of conditions that existed before our solar system formed. The information is real, it is physical, and it is irreplaceable. No future telescope, no matter how sensitive, will ever measure those conditions again from a different angle or at a different time. This is the only light we will ever receive from TON 618's active quasar phase. We cannot request a second observation from a different epoch. What we have is what we have, and what we have is extraordinary. There is also the matter of what TON 618 represents for the broader question of cosmic structure. The most massive black holes are found at the centers of the most massive galaxies. The galaxy hosting TON 618 has not been observed in detail because the quasar outshines it, but based on the expected relationship between black hole mass and host galaxy properties. The galaxy surrounding TON 618 was presumably one of the most massive systems in the early universe. We are looking not just at an extreme black hole, but at an extreme galaxy forming in an extreme epoch of cosmic history. The 21st century has seen enormous improvements in our ability to study these objects. Large spectroscopic surveys have identified hundreds of high-redshift quasars. Infrared telescopes have extended our ability to detect quasars whose optical light has been redshifted into the infrared by cosmic expansion. The Event Horizon Telescope collaboration has demonstrated that direct imaging of black hole shadows is feasible, at least for nearby objects. Radio telescope arrays have probed the jets produced by some of the most active quasars in detail. Each of these advances adds to the picture. The James Webb Space Telescope, launched in late 2021 and operational from 2022 onward, has opened new windows into the high redshift universe. Its ability to observe in the near and mid-infrared at unprecedented sensitivity has allowed astronomers to study galaxies and their central black holes at earlier and earlier cosmic times. Some of the early science results from this instrument have included the discovery of relatively massive black holes at even higher redshifts than TON 618, reinforcing the picture that black hole growth in the early universe was more rapid and more widespread than earlier models suggested. What remains to be understood is the detailed physical mechanism that made this rapid growth possible. The direct collapse scenario, the Super Eddington accretion scenario, and various hybrid models all have adherents in the research community, and they make different predictions about the population statistics of early black holes and about the properties of their host galaxies. Future surveys and instruments will continue to refine these statistics, and the picture will evolve. In the meantime, TON 618 sits in archived data sets and continues to yield information. Spectra taken with large ground-based telescopes have refined its black hole mass estimate. Studies of its emission line properties have given insight into the physical conditions of the gas surrounding the black hole. Variability studies have tracked changes in its brightness over observational timescales. Though the changes we observe in years correspond to processes occurring over much longer timescale in the source's reference frame, due to the cosmological time dilation caused by its high redshift. At a redshift of approximately 2.2, the light from TON 618 has been stretched by a factor of about 3.2 during its journey to us. This means that light which was emitted as ultraviolet radiation by the hot accretion disk arrives at Earth shifted into visible wavelengths. This redshift is itself part of what makes TON 618 detectable. Its intrinsic ultraviolet emission, shifted into the optical band, allowed photographic surveys to capture it as a bright point source even from across billions of light years. The original discovery in 1957 was serendipitous in the way that many important discoveries are. The astronomers conducting the Tonantless survey were cataloging faint blue stellar objects. They were not specifically looking for quasars, because the theoretical framework for understanding quasars had not yet been developed at that point. The survey simply recorded what the photographic plates captured, and object number 618 in that catalog happened to be one of the most luminous quasars in the sky. Its unusual properties were noted but not explained for years afterward. The identification of quasars as a class of extragalactic objects powered by supermassive black holes came through the work of multiple researchers during the 1960s. The recognition that some of these quasars harbored the most massive black holes in the observable universe came later still, as instrumentation improved and theoretical understanding matured. The fact that the object was sitting in a catalog since 1957, before anyone understood what it was, is a useful reminder that our observations consistently outpace our interpretive frameworks. We record data. We build theories. The data often contains implications that our current theories are not yet equipped to process, and it takes time, sometimes decades, for the observations and the understanding to fully converge. Science does not move in a straight line toward complete knowledge. It moves through cycles of observation, hypothesis, experimental test, and revision. TON 618 has passed through several such cycles since its discovery. Its classification as a quasar, its identification as an ultramassive black hole, the refinement of its mass estimate, the recognition of its role in constraining black hole growth models in the early universe. Each of these represented a step in a still ongoing process of understanding. What we currently know is this: a black hole with 66 billion solar masses formed within the first few billion years of the universe's existence. It fed at an extraordinary rate during an era when galaxies were young and gas supplies were abundant. It shone with a luminosity of 140 trillion times the sun's output, making it visible across most of the observable universe. And the light from that activity has been traveling through space for over 10 billion years to reach our instruments today. What we do not yet fully know is how exactly it grew so fast, what the precise physical conditions were in its host galaxy during that period, and what state it is in right now, in this actual moment, as you encounter these ideas. The present-day TON 618 is, by the fundamental physics of light propagation through space, permanently outside our observational reach. Its current state belongs to a category of knowledge that is not merely unknown but unknowable with any technology, no matter how far advanced. That is a sharp constraint. It is not uncertainty about a measurement we could make better. It is a hard limit imposed by the finite speed of light and the vastness of cosmic distances. The present is inaccessible. We work with what light has brought us, which is an extraordinarily rich historical record, but it is a record nonetheless. We are archaeologists of the cosmos, working always from evidence of what was, never direct observation of what is. What is happening at the location of TON 618 right now may or may not be dramatic. The black hole is certainly still there. Whether anything is actively falling into it, whether an accretion disk remains, whether jets are being produced, whether the surrounding galaxy is undergoing any significant evolution, all of this remains outside any possible observation for billions of years to come. The universe is larger and older than intuition handles well. Objects like TON 618 are useful not because they are nearby or because they tell us something about our local cosmic neighborhood, but because they define the extremes of what the universe produces. They show us the upper limits of the mass spectrum, the peak luminosities, the fastest growth rates, the most energetic epochs. They calibrate our understanding of what physics allows. And they are a reminder that our observable universe, vast as it is, contains within it only a fraction of what exists, and within what we can observe we can only see the past. The universe as it actually is, right now, simultaneously in its entirety, is a picture no observer anywhere can ever possess. Every observer everywhere sees only their own backward light cone, their own particular slice of history, their own limited access to a universe that is always and everywhere ahead of what the light has told them. TON 618 is an extreme example of this general truth, but it is the same truth that applies when you look at any star, any galaxy, any distant light in the sky. You are always, without exception, looking into the past. The deeper you look, the farther back you go. If you want to understand the current state of research into the most extreme objects in the early universe, there are several active lines of investigation worth following. Surveys with large spectroscopic instruments continue to identify new high-redshift quasars, extending the census of early black holes and refining the mass function. Studies with the James Webb Space Telescope are probing the host galaxies of quasars in previously inaccessible detail, revealing how star formation and black hole growth interact in early galactic systems. Theoretical work on black hole formation in the early universe continues to develop models of direct collapse and super Eddington accretion that could explain the observed masses. And gravitational wave astronomy, still in its early stages, opens the prospect of detecting signals from the merger of ultramassive black holes in the future, which would provide entirely new information about these objects independent of electromagnetic observations. The field is active, the questions are real, the constraints are tight, and the data is accumulating. TON 618, catalogued incidentally in 1957 as a faint blue dot on a photographic plate, remains one of the most scientifically productive objects in the known universe. If this kind of deep exploration of how science works and what the universe actually contains is the kind of content you want more of, taking a moment to support this channel makes a real difference in allowing it to continue. The history of how we learn what we know, the instruments, the methods, the mistakes, and the moments of genuine breakthrough is at least as interesting as the results themselves. There is one more aspect of TON 618 worth sitting with. The fact that we know it exists at all, that we can measure its mass to this precision, that we can reconstruct the physics of its accretion disk from light that has traveled for over 10 billion years, is itself not obvious. The universe did not come with an instruction manual. The relationship between the time delay in emission line responses and the orbital dynamics of gas clouds around a black hole had to be worked out theoretically and then verified observationally. The techniques had to be invented, tested, applied. The instruments had to be built and pointed in the right directions. The data had to be analyzed and interpreted and checked by independent teams. The knowledge that TON 618 harbors one of the most massive black holes in the observable universe is the product of accumulated work by many researchers across multiple decades, using instruments ranging from photographic plates in the 1950s to modern charge-coupled device spectrographs on 10-meter class telescopes. That is itself a story worth appreciating. The universe is not shy about producing extreme objects. It operates at scales that dwarf any human reference point. Black holes at the centers of distant galaxies accrete matter and radiate energy at rates that challenge our ability to construct meaningful mental models. The numbers involved resist intuition in the same way that certain mathematical truths resist visualization. We can state them clearly and reason about them rigorously, but we cannot picture them in any direct sense. What we can do is track the evidence, refine the measurements, test the models, and keep asking better questions. TON 618, 66 billion solar masses in the ancient heart of a distant galaxy, shining with the light of 140 trillion suns, its ancient signal still crossing the universe toward us, is one of the clearest examples we have of the universe operating at its most extreme. And it raises questions that continue to drive some of the most interesting work in contemporary astrophysics. What formed the first black holes? How fast can they grow? What limits their growth? How do they shape the galaxies around them? What were the conditions in the very early universe that made objects like this possible? These are not merely academic questions. They are questions about the history of structure in the universe, about the physical laws that govern matter and energy at their limits, and about the relationship between the small-scale physics of quantum fields and the large-scale dynamics of cosmological structure formation. The answers, when they come, will change how we understand the universe's early chapters. And Ton 618, visible from across the cosmos, will remain part of that story. To fully appreciate what makes Ton 618 a uniquely important object in modern astronomy, it helps to step back and look at the entire history of how scientists came to understand that black holes could grow to such extraordinary sizes. The path from theoretical curiosity to confirmed cosmological phenomenon spans most of the 20th century, and the story of that intellectual journey is inseparable from the science itself. The concept of an object so massive and so compact that even light could not escape its gravity was first articulated seriously in the late 18th century. The English clergyman and natural philosopher John Michell, writing in 1783, described what he called dark stars. He recognized, using Newtonian mechanics, that if you compressed enough mass into a small enough space, the escape velocity from its surface would exceed the speed of light. In that case, he reasoned, no light could escape, and the object would be invisible to outside observers. The idea was independently rediscovered by the French mathematician Pierre-Simon Laplace a decade later, but then largely forgotten as wave theories of light made the concept seem less applicable. It was not until Einstein's general theory of relativity, published in 1915 and 1916, that the concept of what we now call a black hole was placed on rigorous theoretical footing. Almost immediately after Einstein published his field equations, the German physicist Karl Schwarzschild found an exact solution describing the gravitational field around a perfectly spherical, non-rotating mass. This solution contained a singularity at a specific radius now called the Schwarzschild radius, corresponding precisely to what would later be understood as the event horizon. Schwarzschild derived this while serving on the Eastern Front during the First World War and died shortly afterward from illness contracted at the front. The solution that bears his name is the foundation of all subsequent black hole physics. For decades after this, the Schwarzschild solution was treated primarily as a mathematical curiosity. Most physicists assumed that no real physical object would ever achieve the conditions required for the formation of an event horizon. The collapse of a massive star would surely halt before reaching that point, they believed, due to some physical mechanism that would intervene. It took further theoretical work in the 1930s through 1960s by researchers including Subramanian Chandrasekhar, J. Robert Oppenheimer, Hartland Snyder, and later Roger Penrose and Stephen Hawking, to establish that the formation of black holes was not merely possible but inevitable under certain physical conditions. By the early 1960s, radio astronomers were observing point-like radio sources that defied easy classification. These objects were bright in radio wavelengths but appeared as faint star-like points in optical images. When spectroscopic observations were made of some of them in the early 1960s, the spectra were uninterpretable. The emission lines did not match any known element at the expected wavelengths. In 1963, the Dutch-American astronomer Martin Schmidt was studying one of these objects, designated 3C273, and realized that the strange spectral pattern made perfect sense if the emission lines were the familiar hydrogen lines shifted enormously toward longer wavelengths by the cosmological redshift. If 3C273's redshift was real and cosmological, the object was at an enormous distance, which meant it had to be extraordinarily luminous to appear as bright as it did in the sky. Quasi-stellar objects, soon shortened to quasars, were recognized as a new class of phenomena, and within a few years, the consensus emerged that they were powered by supermassive black holes in the centers of distant galaxies. The understanding that quasars were the most luminous persistent sources in the universe, and that they were concentrated at high redshifts corresponding to the universe's early history, raised an immediate question. How did the black holes powering them get so massive so quickly? This question has been debated ever since and remains a genuinely open problem. The discovery of objects like Ton 618, with measured masses of 66 billion solar masses at a look-back time of over 10 billion years. Gives the question sharp empirical teeth. These are not theoretical objects or extrapolated predictions. They are measured, confirmed, and their existence must be explained by any complete theory of early universe structure formation. One concept that has become increasingly central to explaining ultramassive black holes is the idea of direct collapse black holes, sometimes abbreviated as DCBHs. In the standard picture of the universe's early structure formation, the first objects to form were small dark matter halos, regions where the density was slightly above average and gravitational attraction began to pull in surrounding matter. Within these halos, gas collected and eventually cooled to form the first stars. These first stars, sometimes called population 3 stars, are believed to have been extremely massive compared to typical stars today, because the gas from which they formed contained almost no elements heavier than hydrogen and helium. Without the cooling effects of heavier elements, the gas clouds could not fragment as efficiently, leading to very massive stars that then collapsed at the end of their short lives to form black holes with masses of perhaps 100 to 1,000 solar masses. This provides a starting point, a seed black hole, but growing from a few hundred solar masses to 66 billion solar masses within 3 billion years, even with continuous Eddington rate accretion, is extremely challenging. The numbers strain the limits of what the standard model allows. The direct collapse scenario bypasses this bottleneck by proposing a different formation pathway. Under specific conditions, which include the presence of strong ultraviolet radiation that prevents molecular hydrogen from forming and cooling the gas prematurely, a massive primordial gas cloud can resist fragmentation entirely. Instead of breaking up into smaller clumps that form individual stars, the entire cloud remains a single coherent mass and collapses directly under its own gravity into a single enormously massive object, which then continues to collapse into a black hole. This direct collapse black hole could start with an initial mass of 10,000 to 100,000 solar masses, or potentially even more. This head start makes reaching tens of billions of solar masses within a few billion years much more plausible. The conditions required for direct collapse are stringent, which means such events would have been rare. But the early universe was a very large place, and rare events that occur many times across a large enough volume still leave their signatures in the statistics of observed objects. Whether the most massive quasars we observe today are the descendants of direct collapse black holes is one of the key questions driving current theoretical and observational work. Another dimension of the problem involves the role of galaxy mergers. When two galaxies collide and merge, as frequently happened in the dense early universe, their central black holes eventually spiral together and merge as well. This process is not instantaneous. The two black holes first form a binary system, gradually losing orbital energy through dynamical friction with surrounding stars and gas, then eventually reaching separations small enough for gravitational wave emission to drive the final merger. The resulting merged black hole has a mass close to the sum of the two progenitor masses. A history of multiple mergers could contribute significantly to building up the mass of ultramassive black holes. The problem is timing. Mergers take time to complete, and the first billion years of the universe may not have allowed enough time for a sufficient number of mergers to produce the observed masses. Accretion appears to be necessary in addition to, or perhaps even more important than, mergers in explaining objects like TON 618. The exact balance between these two growth channels is an active research topic. Gravitational wave astronomy offers a future window into this question that is not yet available but is approaching. The merger of two massive black holes produces gravitational waves, ripples in spacetime that propagate outward at the speed of light. The ground-based detectors that made the first gravitational wave detections of stellar mass black hole mergers beginning in 2015 are not sensitive to the very low-frequency gravitational waves that would be produced by mergers involving supermassive or ultramassive black holes. But a planned space-based gravitational wave observatory called LISA, the Laser Interferometer Space Antenna, would be sensitive to exactly these lower frequencies. If LISA is successfully built and deployed, it could detect gravitational waves from supermassive black hole mergers across much of the observable universe. This would provide direct evidence of how often these mergers occur, at what epochs they are most common, and what the mass distribution of merging black holes looks like. Combined with electromagnetic observations of quasars and host galaxies, this data could significantly constrain the competing models of black hole growth. There is also the growing field of pulsar timing arrays, which use the extremely stable rotational periods of pulsars as a cosmic timing reference. Gravitational waves passing through the galaxy distort the arrival times of pulsar signals in characteristic ways. By monitoring arrays of pulsars distributed across the sky, researchers can detect the gravitational wave background produced by the integrated contribution of all supermassive black hole mergers across the observable universe throughout cosmic history. Evidence for this gravitational wave background was reported in 2023 by several pulsar timing array collaborations, representing a new independent line of evidence for the cosmological population of supermassive black hole mergers. The accretion physics of quasars is itself an enormous area of active investigation. The accretion disk around a black hole like TON 618 is not a simple flat ring of uniformly distributed gas. It is a complex, turbulent, magnetized plasma in which magnetic field instabilities called magnetorotational instabilities drive angular momentum outward while driving mass inward. These instabilities generate turbulent viscosity that enables the accretion flow to work. In some regimes, strong magnetic fields threading the black hole can extract rotational energy from the black hole itself, producing the powerful relativistic jets observed in many active galactic nuclei. Understanding the detailed microphysics of accretion flows, particularly in the high luminosity regimes relevant to quasars like TON 618, requires combining radiation magnetohydrodynamics with general relativistic effects near the black hole. Simulations of this complexity require significant computational resources and make predictions about the efficiency of energy conversion from infalling mass to radiated energy, the geometry of the emission regions, the variability patterns of the luminosity, and the conditions under which jets form and are sustained. The luminosity of TON 618 translates to an energy conversion efficiency that is actually quite remarkable. A black hole accretion disk can convert mass into radiated energy with an efficiency of approximately 6 to 42%, depending on the black hole's spin rate. This is dramatically more efficient than nuclear fusion, which converts about 0.7% of mass into energy. The accretion process is among the most energetically efficient mechanisms the universe has produced for converting rest mass into radiation. For TON 618 at its peak luminosity of 140 trillion solar luminosities, and assuming a typical efficiency, the mass being consumed per unit time corresponds to an accretion rate of tens to hundreds of solar masses per year. That means the black hole was consuming material at a rate equivalent to tens to hundreds of stars like our Sun every year, converting a large fraction of that material's mass directly into radiation and expelling it across the cosmos. The total energy emitted by TON 618 during its quasar phase, integrated over the full duration of active feeding, represents an enormous fraction of the rest mass energy of whatever gas was consumed. This energy did not simply disappear. It heated and ionized gas throughout the host galaxy and potentially into the surrounding intergalactic medium. It drove outflows of gas that may have contributed to enriching the environment surrounding the galaxy, with heavy elements synthesized in stars and processed through the accretion disk. It shaped the thermal and chemical state of the medium around the galaxy on scales of millions of light years. The concept of AGN feedback, where AGN stands for active galactic nucleus, encompasses all the ways in which the energy released by an accreting supermassive black hole influences the larger environment around it. At the scale of ton 618, this feedback would have been operating at peak intensity during the quasar phase. Models of galaxy formation and evolution that do not include this feedback consistently predict too many massive galaxies forming too many stars in the early universe compared to what is actually observed. Quasar feedback is now considered a necessary ingredient in producing realistic simulated universes that match the statistical properties of the observed galaxy population. Beyond feedback, quasars like ton 618 also serve as extremely powerful background light sources for probing the intervening intergalactic medium. As the quasar's light travels from its source toward us across over 10 billion light-years of space, it passes through clouds of intergalactic hydrogen gas. These gas clouds absorb the quasar's light at specific ultraviolet wavelengths, and the pattern of absorption features in the observed spectrum encodes detailed information about the distribution, temperature, density, and metallicity of gas along the entire line of sight. This technique, called the Lyman alpha forest because of the characteristic pattern of absorption lines associated with the Lyman alpha transition of hydrogen, has been used to map the large-scale structure of the universe at high redshift and to study how the intergalactic medium evolved between the era of reionization and the present. The epoch of reionization itself is one of the major frontiers in observational cosmology. After the Big Bang, as the universe expanded and cooled, hydrogen atoms formed and the universe became neutral. This is the state captured in the cosmic microwave background, the oldest light we can observe, from approximately 380,000 years after the Big Bang. Over the following hundreds of millions of years, the universe remained neutral while the first stars and black holes were forming. Then, as these first sources of ultraviolet radiation ignited, they began ionizing the surrounding hydrogen, gradually transforming the intergalactic medium from neutral to ionized. This transition, reionization, was completed by roughly 1 billion years after the Big Bang, perhaps somewhat later in some models. Understanding exactly what sources drove reionization and how the process proceeded spatially and temporally is an active research frontier. Early quasars like ton 618 contribute ionizing photons to the intergalactic medium, and characterizing their contribution compared to the contribution from early star-forming galaxies is part of the reionization puzzle. The James Webb Space Telescope is providing new data on galaxies at the epoch of reionization, and this data combined with existing quasar observations is gradually sharpening the picture. The context of large-scale structure is also relevant to understanding ton 618 and objects like it. The most massive black holes do not form randomly throughout the universe. They form in the densest environments, at the intersection of the cosmic web's most massive dark matter filaments, where the flow of gas is most concentrated and the rate of galaxy mergers is highest. The galaxy hosting ton 618 was presumably embedded in one of the largest and densest overdense regions in the early universe, the protocluster that would eventually become one of the most massive clusters of galaxies in the modern universe. Clusters of galaxies are the largest gravitationally bound structures in the universe. They contain hundreds to thousands of galaxies, along with enormous amounts of hot gas visible in X-ray wavelengths and the dark matter that holds them together gravitationally. The most massive clusters contain total masses of hundreds of trillions of solar masses. The cluster-scale environment shapes the growth of its member galaxies, including the feeding history of their central black holes. Identifying and characterizing the large-scale environment around high-redshift quasars is an active research program that uses galaxy redshift surveys and various tracer populations to map the surrounding structure. This work connects the study of individual extreme objects like TUN 618 to the broader cosmological study of structure formation and dark matter distribution. The mass of TUN 618's black hole also places it in an interesting theoretical context with respect to black hole thermodynamics. Stephen Hawking showed in 1974 that black holes are not perfectly black in the quantum mechanical sense. The combination of general relativity and quantum field theory implies that black holes emit thermal radiation, now called Hawking radiation, at a temperature inversely proportional to their mass. For stellar mass black holes, this temperature is so low as to be completely undetectable. For TUN 618's 66 billion solar mass black hole, the Hawking temperature is even lower, on the order of 10 to the negative 20 degrees Kelvin above absolute zero, unimaginably cold. The Hawking radiation power emitted by such a massive black hole is utterly negligible compared to even the cosmic microwave background radiation that bathes the universe. In the extremely far future, after the universe has expanded and cooled far below its current state, after all stars have burned out and all stellar remnants have undergone various forms of decay, black holes will be among the last macroscopic structures to persist, and even they will eventually evaporate through Hawking radiation. For a black hole of TUN 618's mass, the evaporation timescale is approximately 10 to the 103 years, a number so large it requires scientific notation to write and is incomprehensible to visualize. The current age of the universe, 13.8 billion years, is approximately 10 to the 10 years. The evaporation time for TUN 618's black hole is 10 raised to the 93rd power times longer than the current age of the universe. These numbers highlight how different the physics of very massive black holes is from anything in ordinary human experience. The timescales involved, the energies involved, the spatial scales involved, all operate in regimes where our evolved intuition about the world provides essentially no useful guidance. The only tools that work in these regimes are mathematics and the experimental record of observations. For students and scientifically curious individuals encountering these ideas for the first time, the natural question is how one goes about building a career studying these objects. The field of observational astrophysics, particularly the study of high redshift quasars and their host galaxies, draws on skills in optical and radio instrumentation, spectroscopic data analysis, computational modeling, and theoretical physics. Graduate programs in astronomy and astrophysics at universities around the world offer paths into this research. The field is genuinely international, with major observatories and theoretical groups distributed across North America, Europe, Japan, Chile, Hawaii, and increasingly across Asia and Australia. The observations themselves are made with a combination of space-based facilities including the Hubble Space Telescope, the James Webb Space Telescope, the Chandra X-ray Observatory, and the XMM Newton X-ray Telescope, as well as ground-based facilities including the Keck Observatory in Hawaii, the Very Large Telescope in Chile, the Giant Magellan Telescope, an extremely large telescope currently under construction, and the Atacama Large Millimeter Array in Chile for submillimeter observations. Radio observations use facilities like the Very Large Array in New Mexico and the global network of radio telescopes that can be linked together for very long baseline interferometry, achieving angular resolutions that allow direct imaging of structures on scales relevant to active galactic nuclei. The combination of data from all these different wavelength regimes gives astronomers a much more complete picture of any given quasar than any single instrument could provide. TUN 618 and objects like it have been studied across the electromagnetic spectrum, and the multi-wavelength data combined with theoretical modeling gives the detailed physical picture that makes statements about 66 billion solar mass black holes and 140 trillion solar luminosities possible. The numbers associated with TON 618 are extreme by any measure, but it is worth noting that TON 618 is not unique. It is among the most extreme members of a population of ultramassive quasars that has been growing steadily as surveys become more comprehensive. The discovery of additional objects with masses in the range of tens of billions of solar masses at high redshifts is now a routine, if scientifically significant, occurrence. Each new detection adds to the statistics, sharpens the constraints on formation models, and reinforces the picture that the early universe was capable of producing these monsters with relative regularity given the right conditions. The statistical properties of the quasar population, how the number density of quasars of different luminosities evolved over cosmic time, how the mass function of black holes at quasar centers evolved, how the relationship between black hole mass and host galaxy properties evolved. All of this constitutes the observational basis for constraining theories of galaxy formation and evolution over the full span of cosmic history. TON 618 is a landmark in this landscape, a data point at an extreme corner of parameter space that any successful theory must account for. What all of this ultimately points toward is a universe far more productive of extreme structures than anyone suspected before the era of systematic quasar surveys and large-scale redshift measurements. The universe is not merely large. It is extremely active, at least on cosmological timescales, and it operates across ranges of scale and energy that require entirely new conceptual frameworks to appreciate. TON 618 is one of the clearest demonstrations of this. A single object embodying more mass than 66 billion suns, shining with the power of 140 trillion, located at a distance across which light must travel for over 10 billion years, and understood through the combined effort of generations of scientists using instruments that range from glass plates in the middle of the 20th century to orbiting infrared telescopes in the early 21st. The dot on a photographic plate from 1957 turned out to be one of the most massive objects ever measured. That discovery, emerging from systematic observation and careful analysis over decades, is a capsule summary of how science works at its best. Not through sudden insight alone, but through patient accumulation of data, honest reckoning with what it means, and willingness to revise understanding when the evidence demands it. The universe does not make itself easy to understand. It does not organize its extremes conveniently close to Earth where we can examine them in detail. It places them at the far edge of what we can observe, separated from us by time as much as by space, visible only through ancient light that encodes a distant past. But it has given us, apparently inadvertently, physical laws that are consistent across all those distances and all those ages, so that the same equations that govern matter and energy on Earth apply equally in the accretion disk of a 66 billion solar mass black hole 10 billion light years away. That consistency is what makes astrophysics possible. That consistency is what makes the numbers meaningful. And so the light continues arriving. Photons that left TON 618 when the universe was 3 billion years old, that traveled through the formation of our solar system and the entire history of life on Earth, that completed their journey in the era of modern telescope technology, carrying information, encoded in their frequencies and their statistical patterns, about the most extreme object we have so far found. We decode what we can. We build the best models available with current tools, and we ask better questions. That process will continue for as long as there are people who find the universe interesting, which seems likely to be a very long time indeed. To understand the full significance of objects like TON 618, it also helps to understand the larger framework within which cosmologists and astrophysicists operate. The study of supermassive black holes at the centers of galaxies is not isolated from other questions about how the universe works. It is deeply intertwined with the study of dark matter, dark energy, the formation of the first stars, the reionization of the intergalactic medium, the buildup of heavy elements in the cosmos, and the thermodynamic evolution of the universe from its extremely hot and dense early state to the relatively cool and dilute state it occupies today. Dark matter plays a foundational role in this story. The current leading cosmological model, called lambda-CDM, or the Standard Model of Cosmology, posits that the universe's matter content is dominated by cold dark matter, a form of matter that interacts gravitationally but not electromagnetically. It neither emits nor absorbs light. Its existence is inferred from its gravitational effects, including the dynamics of galaxies, the lensing of background light by galaxy clusters, and the detailed pattern of temperature fluctuations in the cosmic microwave background. In this framework, the large-scale structure of the universe formed hierarchically. Small dark matter halos formed first through gravitational collapse of density perturbations. These small halos merged into larger halos over time. Galaxies formed inside these dark matter halos, with the ordinary visible matter, baryons, falling into the gravitational potential wells created by the dark matter. The most massive dark matter halos accumulated the most baryonic matter, leading to the most massive galaxies and the most rapidly growing central black holes. For TON 618 to have grown to 66 billion solar masses within 3 billion years, it must have been hosted by one of the most massive dark matter halos that existed in the universe at that time. The halo mass function, which describes how many halos of each mass exist at each cosmic epoch, is well constrained by cosmological simulations and observations. At the mass scale required to host an object like TON 618, the halos are rare. That rarity is consistent with TON 618, being one of the most extreme objects we find among the entire population of high-redshift quasars. The connection between dark matter halo mass and black hole growth is not direct. Dark matter itself does not fuel the accretion disk. What matters is the baryonic gas that collects in the halo and eventually funnels toward the galaxy's center. The rate at which gas cools and falls toward the center depends on the density and temperature of the halo's gas, the presence or absence of feedback from star formation and the black hole itself, and the history of mergers the halo has undergone. All of these factors combine to determine how much fuel is available for the black hole at any given time, and how quickly it can grow. Numerical simulations of cosmic structure formation that include all these processes have become increasingly sophisticated over the past 2 decades. Projects like the Illustris simulation, the Eagle simulation, the TNG simulations, and the Simba simulation have modeled the coevolution of galaxies and their central black holes across cosmic time in representative volumes of the universe. These simulations generally reproduce many observed properties of the galaxy population, including the distribution of galaxy sizes, colors, star formation rates, and the relationship between black hole mass and galaxy properties. However, reproducing the most extreme objects, the most massive black holes at the earliest times, remains a challenge. The rarest, most extreme outcomes are difficult to capture in simulations of finite volume. More specialized simulations focusing specifically on the formation of the first massive black holes in overdense environments have been run, and these give some insight into how early formation might have proceeded. But the parameter space is large, and the constraints from observations are still accumulating. One of the most powerful observational constraints comes from the demographics of quasar host galaxies. If the relationship between black hole mass and host galaxy properties seen in the local universe extends back to high redshifts, then the galaxies hosting ultramassive quasars like TON 618 should be correspondingly extremely massive. Measuring the properties of quasar host galaxies at high redshift is observationally challenging, because the quasar itself typically outshines the host, but techniques like careful subtraction of the quasar's point source contribution from imaging data, and the use of wavelength ranges where the host galaxy emission is stronger relative to the quasar, have allowed some measurements to be made. The James Webb Space Telescope has dramatically improved this situation by enabling deep imaging of quasar host galaxies at high redshift, with much greater sensitivity and spatial resolution than was previously possible. Early results have confirmed that many high redshift quasars are hosted in massive, actively star-forming galaxies, consistent with the picture of coevolution, but also revealing some surprises. Some quasar host galaxies appear more compact than predicted by simpler models, and some appear to already have signs of suppressed star formation despite the quasar still being active. These nuances are feeding back into theoretical models and driving refinements. The chemistry of quasar regions is also informative. The emission lines in quasar spectra come from gas that has been enriched with heavy elements by previous generations of stellar evolution. The abundances of different elements relative to each other encode information about the star formation history in the quasar's environment prior to the observed epoch. Observations of high redshift quasars, including TUN 618, show that the gas near the black hole is already significantly enriched with metals, meaning that substantial star formation and stellar evolution had already occurred in the environment before the light we observe left the source. This is consistent with the picture of these systems as the most extreme products of the early universe's most active environments, where both star formation and black hole growth proceeded rapidly from very early times. The X-ray properties of quasars provide additional diagnostics. When accretion disk photons scatter off energetic electrons in the hot corona above the disk, a process called inverse Compton scattering, they gain energy and emerge as X-ray photons. The spectrum of this X-ray emission carries information about the geometry and temperature of the corona, and variations in the X-ray brightness on short timescales provide insight into the size of the emitting region, because only regions small enough to vary coherently can produce observed variability on a given timescale. The X-ray emission from quasars like TUN 618, while faint at Earth due to the enormous distance, is still detectable with powerful X-ray space observatories and continues to be an active area of study. There is also the question of the polarization of quasar light. The geometry of the accretion disk and surrounding structures can produce polarized emission, and measuring the degree and angle of polarization provides constraints on these structures. This is a technically demanding measurement at high redshifts, but has been pursued for a number of bright quasars. The next generation of extremely large ground-based telescopes will significantly improve our ability to make such measurements for faint and distant objects. The study of quasar variability across multiple wavelengths and timescales connects to a technique called echo mapping or reverberation mapping, which was mentioned earlier as the method used to measure TUN 618's black hole mass. The principle of reverberation mapping is elegant. If you observe a quasar's brightness in two wavelength bands that trace regions at different distances from the black hole, you should see a time lag between variability in the inner region and the response in the outer region, because light takes time to travel between them. By measuring these lags for multiple wavelength pairs and emission line species, you can map out the structure of the accretion disk and broad emission line region as a function of radius. This technique effectively uses the variability of the quasar as a signal to probe scales that cannot be directly resolved by any telescope. For TUN 618, the scale of structures being probed is smaller than any telescope could image directly from Earth's position, but reverberation mapping allows the relevant physics to be inferred. The broader context of what these ultramassive black holes mean for our understanding of the universe's fate is also worth considering. though it operates on timescales that dwarf anything in human experience. In the very long-term future of the universe, depending on the equation of state of dark energy and the ultimate fate of cosmological expansion, the universe will continue to evolve. The rate of cosmic expansion is currently accelerating, driven by dark energy. If this acceleration continues as current data suggests, the universe will eventually reach a state where all galaxies outside the local group are receding faster than the speed of light, making them permanently inaccessible. The local group of galaxies, of which the Milky Way and Andromeda are the two largest members, will eventually merge into a single large elliptical galaxy. The supermassive black holes at the centers of the Milky Way and Andromeda, currently 4 million and approximately 100 million solar masses respectively, will eventually merge when the galaxies do, some billions of years from now. This future merger is a reminder that the processes we observe in distant quasars, the feeding, the merging, the growth, were once happening and will happen again in our own galactic environment, albeit on scales far smaller than ton 618. We live in a relatively quiet time in our galaxy's history, in an era when the most extreme activity has subsided, but the long-term dynamics of structure formation continue. The entire subject of supermassive and ultramassive black holes intersects with fundamental questions about the nature of spacetime and the completeness of general relativity. Inside a black hole's event horizon, the mathematics of general relativity predicts the existence of a singularity, a point of infinite density and curvature. Most physicists believe that this singularity is not physical, but rather represents the breakdown of general relativity in a regime where quantum effects become important. A complete theory of quantum gravity would be needed to describe what actually happens at the center of a black hole, and no such theory currently exists in a complete and tested form. Various candidate approaches, including string theory, loop quantum gravity, and other frameworks, make different predictions about what replaces the classical singularity in a quantum gravity description. Some proposals suggest that the singularity is replaced by a Planck density object of some kind. Others suggest that the information falling into the black hole is preserved in some form and eventually re-emitted through Hawking radiation in a highly scrambled state. The black hole information paradox, which asks whether the process of black hole formation and evaporation is consistent with the principle of unitarity in quantum mechanics, remains one of the deepest open problems in fundamental physics. None of these deep theoretical questions affect our ability to measure the mass of ton 618 or to characterize its quasar emission. General relativity works extremely well at the scales relevant to accretion disk physics and event horizon scales. But they are part of the broader scientific context within which black holes of all masses are studied, and the extreme objects at the top of the mass scale, like ton 618, represent the most extreme test cases available for any future theory that seeks to describe gravity across all scales. What is remarkable about all of this, taking a step back to appreciate the full sweep of the subject, is how much has been learned from the light of a single photographic dot identified in 1957. The spectroscopic measurements, the variability studies, the reverberation mapping campaigns, the multi-wavelength survey data, the cosmological redshift measurements, the theoretical modeling of accretion physics, the large-scale structure simulations, the deep imaging of quasar fields. All of this work has transformed that anonymous blue dot into one of the most thoroughly characterized extreme objects in the observable universe. The progress required the development of entirely new instrumental capabilities. Charge-coupled device detectors replaced photographic plates, improving sensitivity by orders of magnitude and enabling precise digital photometry. HL spectrographs with sophisticated optical designs enabled high-resolution spectral measurements of faint sources. Adaptive optics systems corrected for atmospheric turbulence, improving the sharpness of ground-based telescope images. Digital sky surveys like the Sloan Digital Sky Survey cataloged hundreds of millions of objects and enabled statistical studies of quasar populations impossible with earlier targeted observations. Space-based telescopes operating in ultraviolet, X-ray, and infrared wavelengths provided windows onto the universe that Earth's atmosphere otherwise blocks. Each of these technological developments was itself the product of decades of engineering, physics, and materials science research. The people who built the instruments that measured Ton 618's black hole mass were not necessarily focused on Ton 618. They were building better tools for astronomy in general, and the better tools revealed better answers to questions that could not even be properly formulated with earlier instruments. This is the character of scientific progress in astronomy. It is driven by the interplay between theoretical questions, observational capabilities, and technological development. The questions motivate the instruments. The instruments reveal new phenomena. The new phenomena drive new questions. The loop continues. We are currently at a point where the questions being asked about the early universe and the first supermassive black holes are sharper than they have ever been, and the instruments being built to address them are more powerful than any that have existed before. The extremely large ground-based telescopes under construction, with mirror diameters of 30 meters and larger, will collect vastly more light than current facilities, enabling spectroscopic studies of quasar-host galaxies and emission line properties at redshifts and sensitivities currently inaccessible. The James Webb Space Telescope will continue returning data for many years. Planned X-ray observatory concepts would extend our ability to study quasar X-ray emission to much greater distances. The gravitational wave observatories, both the existing ground-based detectors and the planned space-based LISA mission, will add an entirely new observational channel that is completely independent of electromagnetic radiation. Gravitational waves pass through matter without being absorbed or scattered, meaning they can provide information about events in regions that are opaque to light, and they propagate across the universe without the complications of cosmological evolution, affecting their interpretation in the same ways that affect photons. The picture being assembled from all these efforts is one in which black holes are not peripheral to the story of cosmic evolution, but central to it. They formed early, grew rapidly, shaped the galaxies around them, and the cumulative effect of this growth and feedback determined the properties of the galaxy population we observe today. The most extreme members of the black hole population, the ultramassive objects at the top of the mass spectrum, represent the outcome of the most extreme versions of these processes operating in the most extreme environments the early universe produced. Ton 618 stands at the top of this hierarchy among confirmed, well-measured objects. Its 66 billion solar mass black hole is not merely a curiosity or a record for its own sake. It is a physical system that encodes information about the conditions of the early universe, the physics of accretion at extreme rates, the formation of structure in the cosmic web, and the limits of what the laws of physics as we understand them permit. And it is sitting there, 18.2 billion light-years away, its present state invisible to us and inaccessible for billions of years, while the ancient light from its quasar phase continues to bring us the only report we will ever have from its history. There is something both humbling and energizing about this situation. Humbling because the universe vastly exceeds the scale at which direct observation is possible, and because the fundamental speed limit of light means that our observational window on the cosmos is always a window into the past, never the present. Energizing because, despite these constraints, careful and creative science has managed to extract an extraordinary amount of knowledge from the limited information available. The mass of a black hole 10 billion light-years away, measured to within a factor of a few, from the time delays and velocity widths of spectral emission lines. The temperature of the accretion disk, inferred from the spectral energy distribution of the emitted radiation. The history of gas enrichment, read from the elemental abundances in the emission line spectra. These are remarkable achievements, and they represent the cumulative effort of many researchers, many instruments, many calculations, many revisions, and many decades of work. The story of what we know about Ton 618 is, in miniature, the story of how modern cosmology and astrophysics developed as scientific disciplines. If you have followed this far, through the scale of the event horizon and the mass in solar units and the look-back time and the accretion physics and the theoretical puzzles and the observational techniques and the broader cosmological context, you have engaged with real science at a serious level. The ideas covered here are not simplified beyond recognition. They represent the current state of knowledge, expressed as clearly and accurately as the subject permits. The universe is a place of extraordinary scale, extraordinary age, and extraordinary physical processes. Objects like Ton 618 are the universe operating near its limits. Understanding them is not merely an academic exercise. It is part of understanding where we are, what the universe we inhabit actually is, and how the conditions that led to the existence of everything we know came about. The ancient light keeps traveling. More of it will arrive tonight, and tomorrow, and every day that follows, carrying its message from the edge of the observable past. We keep looking, keep measuring, keep building better instruments and better theories. The conversation between human curiosity and the universe's offerings continues, as it has for as long as people have looked up at the sky and asked what they were seeing. Ton 618 will be part of that conversation for a long time to come. There is one more dimension to this subject that deserves careful attention, and it connects the very large to the very small in a way that reveals something fundamental about the nature of physics itself. The behavior of matter and energy near the event horizon of a black hole as massive as Ton 618 is governed by general relativity, and general relativity is extraordinarily well tested. The predictions it makes about the bending of light, the slowing of clocks in gravitational fields, the precession of orbital ellipses, the existence of gravitational waves, and the behavior of spacetime around compact objects have been confirmed to extraordinary precision across many independent experiments and observations. What is unusual about the environment near Ton 618's event horizon is not that the physics is different. The physics is the same. What is unusual is the scale at which familiar effects manifest. Near the event horizon of a stellar mass black hole, tidal forces are so extreme that any object approaching the horizon would be stretched vertically and compressed laterally in a process graphically described by the term spaghettification. An astronaut falling toward a stellar mass black hole would be torn apart long before crossing the horizon. For Ton 618's event horizon, the situation is almost paradoxically different. The event horizon is so large, and the tidal forces there so relatively gentle, given that tidal forces scale as the mass divided by the cube of the radius, and the radius grows faster than the mass for very massive black holes, that a hypothetical observer crossing Ton 618's event horizon would not experience anything immediately dramatic. The spacetime curvature at the horizon is modest by the standards of smaller black holes. The crossing itself would be undetectable from a local physics standpoint. The observer would pass the point of no return without any physical sensation, without any signpost saying this is the boundary. Only later, as they fell deeper inward, would the curvature and tidal forces increase to destructive levels. But the event horizon itself, for a black hole this massive, is not a physically extreme environment in terms of local spacetime curvature. What makes it extraordinary is not local conditions, but topology. Once inside, the geometry of spacetime is such that all future paths lead toward the central singularity. There is no direction that leads out. This is not a force preventing escape. It is the structure of spacetime inside the horizon being such that outward directions simply do not exist in the same way. This thought experiment, combined with the measurement of Ton 618's physical parameters, illustrates how general relativity unifies concepts that seem separate in everyday experience. Mass, geometry, time, and causality are all aspects of a single structure. The event horizon is not a wall but a change in the causal structure of spacetime. Gravity is not a force in the Newtonian sense, but the curvature of spacetime in response to the presence of mass and energy. And the extreme scales at which these relationships manifest in objects like Ton 618 provide some of the most rigorous tests of the theory available. General relativity has passed every test applied to it so far, from the deflection of starlight during solar eclipses, first measured in 1919, to the detection of gravitational waves from merging black holes and neutron stars in the 21st century. It is one of the most precisely tested theories in all of science. But physicists know it cannot be the complete story because it is incompatible with quantum mechanics at the formal level, and because it predicts its own breakdown in the form of singularities. A successor theory must reduce to general relativity in the appropriate limit, just as general relativity reduces to Newtonian gravity in the weak field, low-velocity limit. The extreme environments associated with supermassive black holes like Ton 618 are exactly the kinds of places where deviations from general relativity, if any exist, might eventually be detectable. The measurements being made now with current instruments are consistent with general relativity, but the precision of future instruments may reveal subtle effects that current data cannot detect. This is one reason why pushing observational capabilities to study the most extreme objects in the universe is scientifically valuable beyond the immediate results. The study of black holes has also had an unexpected cultural dimension that is worth acknowledging. The first direct image of a black hole shadow, released by the Event Horizon Telescope collaboration in April 2019, became one of the most widely shared scientific images in history. The image of M87 star, a glowing orange ring surrounding a dark circular shadow, appeared in news outlets, social media, classrooms, and conversations around the world. It connected a large and diverse public audience to a concept that had been theoretical for decades and made real by painstaking technical work by an international team of over 200 scientists. Ton 618 is too far away, and its angular size too small for current event horizon imaging techniques to apply. The angular size of its event horizon as seen from Earth is far smaller than even M87 star's shadow. But future advances in very long baseline interferometry, combining signals from radio telescopes spread across Earth or eventually in space, might eventually extend this imaging capability to more distant objects. The science of imaging black hole shadows is in its infancy, and the next few decades may bring capabilities that are currently difficult to anticipate. In the meantime, the indirect methods, spectroscopy, reverberation mapping, variability studies, multi-wavelength surveys, continue to accumulate information about the population of supermassive black holes across cosmic time. The census of the most massive black holes in the early universe is growing. Each new detection either confirms the existing picture or reveals something that requires theoretical adjustment. The most interesting outcomes are always the unexpected ones. Science makes the most rapid progress when observations reveal something that the current theoretical framework cannot easily accommodate. Objects like Ton 618, growing to 66 billion solar masses in 3 billion years, sit right at the edge of what current theories predict should be possible. If more objects of this mass or larger are found at even higher redshifts, younger cosmic epochs, the tension with theoretical predictions will intensify and force a deeper examination of the underlying assumptions. That examination, when it comes, will likely reveal something true and important about the universe that we do not currently know. It will add to the accumulating picture of how structure forms, how black holes grow, how galaxies evolve, and how the universe arrived at its current state from its initial conditions. That picture is far from complete. The gaps in our knowledge are real, and they are scientifically productive in the sense that they define where new understanding is needed and what observations should be prioritized. Every field of science has its frontier, the edge of what is known, where understanding is incomplete and the measurements are hardest to make, and the theoretical models are most uncertain. In observational cosmology and the study of supermassive black holes, that frontier is currently located in the early universe, in the first few billion years of cosmic history, in the epoch of quasar activity, in the environments of the most extreme objects we have found. TUN 618 marks one of the outermost points on that frontier, a confirmed, measured, real object at the intersection of extreme mass, extreme luminosity, extreme distance, and extreme age. It was there doing what it did 10 billion years before we looked, and we found it, understood something of what it is, and are still working to understand it more fully. The universe does not announce itself. It does not label its wonders or explain its processes. It simply operates according to the laws of physics across all scales and all times, and it is up to us to read the signals it sends, translate them into understanding, and ask the next question. TUN 618 has been sending its signal for over 10 billion years. We have been listening, with increasing sophistication, for less than a century. There is much still to hear. To close with a direct summary of where the science currently stands on TUN 618 and what makes it scientifically significant. It is one of the most massive black holes ever confirmed, with a measured mass of 66 billion solar masses. Its accretion disk, active when the universe was approximately 3 billion years old, produced luminosity equivalent to 140 trillion times the sun's output. Its event horizon spans approximately 2,600 astronomical units in diameter, large enough to contain 40 complete solar systems arranged edge to edge, with light taking 11 days to cross from one side to the other. The light we observe today left TUN 618 over 10.8 billion years ago, meaning its current state is permanently beyond our observational reach for billions of years. Its existence poses genuine theoretical challenges about how black holes could have grown so massive so quickly in the early universe. Those challenges are actively being addressed by research programs spanning multiple observational techniques, large-scale numerical simulations, theoretical work on accretion physics and black hole formation, and emerging new observational channels including gravitational wave astronomy. It was discovered accidentally in 1957, recognized as a quasar over subsequent decades, and measured with modern techniques to reveal its extreme properties. It represents one of the clearest available examples of the early universe operating at its most extreme, and it will remain an important benchmark for cosmological and astrophysical understanding for as long as we continue studying the universe's history. The ancient light from TUN 618 is the only record we have of one of the most extreme systems ever produced by the universe. We will keep reading it as carefully as our tools allow. The deeper you look into the history of any major scientific discovery, the more you appreciate how much of what we know rests on incremental work that was never celebrated as a breakthrough in the moment it happened. The graduate student who wrote reduction software that processed quasar spectra, the engineer who designed the detector that made the measurements possible, the theorist who worked out the relationship between emission line time lags and orbital velocities 20 years before the measurement was applied to an ultramassive quasar. None of these contributions individually produced the knowledge that TUN 618 harbors a 66 billion solar mass black hole, but all of them were necessary. This is the character of science as actually practiced, as opposed to the simplified narrative of lone genius and sudden insight. It is a collective enterprise, distributed across institutions and disciplines and time, producing understanding that no individual could arrive at alone. The knowledge about Ton 618 is, in a real sense, the product of all of human scientific civilization's engagement with the universe over the past several centuries. From the development of the telescope, through the development of quantum mechanics and general relativity and spectroscopy, and digital computing and space-based observation. When we look at the data and say this black hole has 66 billion solar masses, we are drawing on that entire inheritance. The number is not a guess or an estimate in the loose sense. It is a measurement derived from physical principles, validated by independent methods, and consistent with a theoretical framework that has been tested across many other contexts. That is what scientific knowledge means, not certainty in an absolute philosophical sense, but understanding grounded in evidence and tested against the world. And Ton 618, one of the universe's most extreme productions, has been patient enough to send us its light across 10 billion years of cosmic time, waiting for a civilization sophisticated enough to read what it was saying. We are reading it now, and we will keep reading for as long as we can. There are few objects in the known universe that concentrate so many open scientific questions into a single point of light as Ton 618 does. Its existence at the boundary of the observable universe, its formation during the universe's first 3 billion years, the extreme rate at which its black hole grew, and the extraordinary luminosity it achieved during its active phase all make it a convergence point for